n factorial times, I'm going to have a 2n plus 2 factorial on the bottom and a 2n factorial on the top. Is that right? All right. So this is the limit as n goes to infinity. What cancels, what stays? N plus 1 on top. A 2n plus 2 and also a 2n plus 1 on the bottom, right? Because those are off by 2.
Where did 2n plus 1 come from?
All right. Take a look at your small examples. If I look at, for example, n equals 3, what I've got is 6 factorial over 8 factorial, right? 6, 5, 4, 3, 2, 1. And this is 8, 7, 6, 5, 4, 3, 2, 1. Because the structure of the factorial, do you see where everything from n downward cancels out, but I have 2 more terms on here. That's it. So if you weren't careful here, you could get that this thing is equal to a half, but this thing actually goes to 0, right? So you can simplify it one more step if you wanted to. You could say this is just 1 over 2 times 2n plus 1. That definitely goes to 0. But you don't even need this extra step here. All right. So what do we know about 0? What makes that so special? Well, it's less than 1, right? And so it's going to be convergence by ratio test. Just remember that for ratio test, the threshold is a 1. All right. Next one is integral test.
Give us a problem when asked is the integral test within the equation itself does not satisfy the conditions for the integral test?
No. Yes, there's no tricks. Yeah, that I think would be dirty pool. I think you're right. If they give you one and say use the integral test, it's going to have to be workable by integral test. Yeah. And as far as I can tell, the last couple of years I've taught this class, when there was an integral test problem, they told you to use integral test. Just because integral test problems tend to be solvable with some other method, like especially since you've got the 0 infinity case of the limit comparison test, a lot of things you can do with an integral test you can also do with that one. So just to make sure that you know how to do it, we'll probably have one that you have to. All right, so you do, however, have to check. That's the thing. That is always part of the points, is you have to check whether or not it's applicable. Or at least verify that it is. So verify that integral test works. Okay, so what 3 things have to be true? Yep. F is decreasing, and we'll, how do you tell something's decreasing? You look at the derivative. F of x is what? X times e to the negative x squared, I guess is what we're looking at. Okay, so f prime of x is, well, first times derivative of the second, e to the negative x squared times negative 2x, and then second times derivative of the first would be e to the negative x squared. Okay, so what I've got is e to the negative x squared that can be factored out, and I've got 1 minus 2x squared. Okay, now, when is this going to be negative? That's going to be when 2x squared is bigger than 1, right? And so, let's see, even for x equals 1, that's true, right? So as long as x is greater than 1, we're okay. And in this case, we're starting the summation at 2, so no problem, right? And if you see the series start off in a weird place like 3, it's usually to make that part of it work. Okay, so f is decreasing. There's your justification for that. All right, what are the 2 things that it have to be? Yeah, continuous and positive, I think. Yeah, so f is continuous. Basically, just mention it. And it's usually okay, just because we're not doing continuity proofs in here. It's a ratio of 2 things. You might verify that this thing's never 0 on the bottom, so there's no asymptote. f is positive. Why? Because, because x is positive, right? Because I'm summing this from 2 to infinity. Okay, so that part, like I said, I think I graded that last year and it was worth 3 out of the 10 points. So a lot of people got docked because they missed that part. So, all right. Now that we know we can use it, despite the fact that we were told to, let's see. So what I want to check is the integral from 2 to infinity of x e to the negative x squared. What kind of integral is this? Nope. It's a substitution, yeah. Can't do with integration by parts. Because you don't know how to integrate e to the negative x squared, right? That's not a thing that we know. So, let's do a u sub. If you do u equals x squared, that means du is going to be 2x dx. And so, this is the limit from somewhere, let's say u of 2 to u of infinity, whatever that means, of, and you know what? Yeah, let's go ahead and just update our limits. This is going to be the integral from 4 to infinity of e to the negative u du, is that right? Just because when we start at 2, when x is equal to 2, u is equal to 4, and as x goes to infinity, u also goes to infinity.
Could it be like 1/2 though?
Oh, I need 1/2? Yeah, you're right. Okay, fair enough. So, I've got 1/2 integral of e to the negative u, which of course is 1/2 times negative e to the negative u at 4, and let's not be plugging in infinity. I guess let's calculate it as a limit. I know people are picky about that, like myself. So, let's do the limit of c goes to infinity of the integral evaluated at 4 and c. Now this is a limit that c goes to infinity of, now when I plug in c, I get negative 1/2 e to the negative c. And when I plug in 4, I get plus 1/2 e to the negative 4. All right. So, of course, the limit has to go to 0 if this thing's going to converge, and it does. That limit definitely goes to 0. So this whole thing goes to 1/2 e to the negative 4. All right. So what does that tell me about what? There's got to be a punchline to this thing. What are we trying to do here?
Converges.
Determine convergence or divergence. Yeah, all right. So, yeah, it converges. Why? Because this is finite. So, the series converges by the integral test. Now, don't be tempted to write that it converges to this, because it doesn't, right? This is sort of a poor approximation of what it converges to, because you remember the difference between the integral and the series is all those little triangular portions in between the rectangles and the curve. So, all right. So we've got all of that. Okay. Uh-huh. Oh, where did I get this half? From this 2x. What I've got is an x dx, and so it's the same as 1/2 du. So that's where that's coming from, out of the u substitution. A trap that I've seen people fall into is this. A lot of people will say, well, here's the whole exponent, it's negative x squared. So I get negative 2x dx, that's okay. So it means I've got a negative 1/2, but I've got an e to the u. And then they get to this step, and they've got something like this, and they say, well, that integral diverges. Where's the problem with that? There is actually a flaw in it, but it's tough to see. The problem is in your shifting of your limits, I don't go from 4 to infinity anymore. Do you see where I actually go from negative 4 to negative infinity? Because it's a negative x squared. That's a thing. So this is actually the limit of c goes to negative infinity of that, which does end up going to the same place. So you still get 1/2 e to the negative 4, but I've seen people fall in that trap before, assuming that a limit that goes to infinity after you change your limit still goes to infinity. Double check the behavior of what your u substitution is doing. That's why I tend not to put the negative in the x squared in the u substitution, just because I tend to forget about it in there. So, can't say it'll come up on your exam, but it's just something I've seen people mess up in the past. Alright. Okay, I bet you'll have one of these. This is alternating series, determine whether it converges absolutely, conditionally, or not at all. Okay, so what do you want to aim for first, anyway? There's an order that you typically check these things. I would say we can look for a test for divergence, because if it doesn't converge at least conditionally, test for divergence is your only weapon against it. Now these terms do go to zero, right? What's your gut feeling on this? Do you think it's going to be absolute, conditional, or not at all? It's probably going to be conditional, right? If nothing else, just because that's what requires the most work on the test, right? Again, we're jerks. But don't look to us, look at the problem, right? Because if that was 1 over n squared plus 1 or n over n cubed plus 1, it would converge absolutely. It'd be a lot less trouble, right? So, all right, now that we have some idea of what it's going to do, let's go about the point of verifying it. So first, let's say the series does not converge absolutely. I don't think you would say it diverges absolutely, because I don't think that's a thing. I think you would just say it doesn't converge absolutely. So let's prove that. If I look at say an is a term that I've got. What am I going to limit compare that to? Yeah, 1 over n. All right. All right, if I look at the limit as n goes to infinity of an over bn, that is the limit as n goes to infinity of n over n squared plus 1 times n over 1, which is a limit of n squared over n squared plus 1, which is definitely 1. You don't have to do L'Hopital's if they're the same kind of function. Alright. So, we can say, since the sum bn, so 1 over n diverges, you can either quote that it's a p-series with p equal to 1, or you can say that it's a harmonic series. So since that diverges, our series, let's see, n over n squared plus 1 diverges by limit comparison test. And so that means the series in the question, negative 1, n plus 1, n over n squared plus 1, does not converge absolutely. Okay, so that's the first half of it. Now, we've shown that it doesn't converge absolutely. We'd like to show that it does converge conditionally, right? Okay. What test used for that? Gotta be alternating series test. All right, so part 2, the series does converge conditionally. All right, so an is n over over n squared plus 1. And so I've got, you know, power of negative 1 times this guy. What do I need to know about this? I need to know that these terms are decreasing to 0, right? Alright, so claim the sequence AN is decreasing. Again, how would you show that? Some kind of a derivative, right? Alright, if f of x is the function of x corresponding to this, x over x squared plus 1, then f prime of x is quotient rule, right? So bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Alright, and so this is what? 1 minus 3x squared, is that right?
Should be x squared plus 1 squared in the denominator.
Yes. Alright. Now these don't cancel, do they? Oh, it's just 1 minus x squared. Okay. Over x squared plus 1 squared, right? Okay. And that is in fact negative when x is bigger than 1. And our series starts at 2, so we're good. Alright. So it is decreasing. What's the other thing you have to verify? Yep. It has to be decreasing to 0, so the limit as n goes to infinity of an is the limit as n goes to infinity of n over n squared plus 1, which is 0. So the thing converges by the alternating series test. Yeah. So
It's like you kind of do minus dd prime over
mhm.
what is that?
The derivative of high over ho is OD high minus high D ho over ho squared. Right? So bottom times derivative of the top minus top times derivative of the bottom over bottom squared. Alright, I think that's all we got time for because I'm out of time today, but we'll pick the rest of this up and whatever else we can find.